Welcome to the 1951 Nobel Prize in Physics. This one goes to Sir John Douglas Cockroft as well as Ernest Walton. So it was split between those two men. They actually worked together on something. So this was sort of two guys doing one thing. They won for their pioneering work in the transmutation of atomic nuclei by artificially accelerating particles. That sounds familiar. We've had a couple other prize winners who were actually making new elements from old elements, but this time they did it with a much different way. And the other two that won for that same thing were 1938. Fermi won, but he was using natural neutron radiation to produce new elements. 1939, there was the cyclotron that was developed as part of the Manhattan Project, and it is capable of doing some of that, but it's very low energy, so there's not a lot of work that could be done with it. These guys up to the energy level quite a lot, so you could actually get to do some work you couldn't do by these other methods. So this one's a little complicated. We're gonna do a little bit different format in this video than we've done before, but this one is pretty interesting stuff. So let's dive in. So before we get to this prize, we have to look at just how many shoulders that these folks were sitting on at this point. Nuclear physics has resulted in multiple Nobel Prizes, but we're about to have one more. So let's dig in a little bit. Now, Rutherford, who you haven't heard about yet, but actually won the Nobel Prize in Chemistry in 1908, was using alpha particles to study nuclear reactions and had successfully actually turned nitrogen into oxygen. What the heck is an alpha particles? Remember, physics and chemistry, it's kind of their own language. You have to learn it as a student. I had to suffer through it. And it's not hard once you learn the language, like anything else. An alpha particle is essentially two neutrons and two protons stuck together, which sounds suspiciously like the nucleus of a helium atom, because it is. It just happens to be the term used when one results from nuclear decay of a larger element. So it's a fission byproduct that occurs. And you can get them by artificial means by just stripping off the electrons and throwing them at stuff. But typically when you refer to it as an alpha particle, it's as a result of decay. So Rutherford was using alpha particles that were coming from natural sources to do nuclear reactions, way back. Now, you also had Fermi doing it with naturally occurring neutrons, who won the prize in 38. Lawrence, who won the prize for the cyclotron in 39, who also had some limited number of nuclear reactions they could do. But there were very few nuclear reactions that were really possible using alpha particles, and more with neutrons and more with the cyclotron, but those were fission instead of fusion, right? So you really want to look at both sides of this and really understand both the fission side as well as the fusion side, and you want to study it for all elements that are known with all possible reaction chains. That way you really know what you're doing. So let's dig into what these two guys did to sort of open up that envelope a little bit more. Now, I've mentioned a couple of times some of the Nobel laureates and scientists in general stand on the shoulders of giants. Well, in this particular case, we have very strong evidence leading to that. Ernest Rutherford, who you see in the center here, actually encouraged Ernest Walton, who you see on the left, and John Cockcroft, who you see on the right, to build a high voltage accelerator. And what he wanted was more penetrating energy. So the higher energy an alpha particle or proton or a piece of radiation, the more it penetrates through something. So less energetic radiation won't penetrate through anything. Higher energetic radiation will penetrate through more stuff than you want to talk about. And he wanted something with more power, because with more power, you can get newer reactions that you've never seen before with higher energy physics involved. And that high energy physics helps you really understand the world, the nuclear world, quantum mechanics, and all kinds of things we're still trying to figure out today. In fact, the Large Hadron Collider is saying it might not be big enough to do everything they want to do. And the Large Hadron Collider is largely kind of the great-great-grandson of this kind of stuff. But in 1932, they did just that, and they accelerated protons, which is a fancy way of saying the nucleus of a hydrogen atom, and they shot it at lithium, and they caused the nuclei to actually split and produced multiple alpha particles. Now, the Cockroft-Walton generator is basically just a fancy electric circuit that generates a high DC voltage from a comparatively low AC input. Now, I know that's weird language for a second, but remember, alternating current has peaks and valleys. It goes up, it goes down. DC goes up and goes back to zero. It doesn't go from a positive number to a negative number. It just goes up and stays up positive. Whereas alternating current, AC, does exactly that. It alternates. It goes from some peak to a valley, so a peak to a valley. Now, the circuit involves a network of capacitors and diodes to form nodes. And in the picture, you can see a bunch of nodes, those little circle-shaped things. And those nodes, the more of them, the higher the power output of the generator. In fact, the output voltage is comparatively much larger. In fact, that it's 2 times the peak input voltage multiplied by the number of stages. So if you have 2 stages, you get one number. If you have 16 stages, you get a number. If you have 32 stages, you get an even bigger number. So the multi-stage accelerators are very important and very careful. You have to be very careful to control them right, but they can get you to comparatively very high energies compared to what was possible before them. In fact, the one you see in the image here was used during the development of the atomic bomb in the Manhattan Project. So, very important discovery, very important device. It was the one that actually caused the world's first artificial sort of fission reaction. So, they are not ones to be trifled with. These are things to be handled with care in labs. They're not as hard to build as they used to be, but they can be quite dangerous if you try to build one at home, even though the equipment is actually largely available to do it if you so chose. But I don't recommend that. So let's. Now, these generators were actually used in legitimate research labs like Fermilab up until about 2012, I think is when Fermilab finally retired them. But think about that. That was not that long ago that these types of generators are still being used. Now, today we have more efficient ways to get to those energy levels, and in fact, higher ones than that that are being used at labs all over the world. But it was certainly an invention that for its time was just important. We needed it. We had to have it, and had to have something like that. And it served its purpose. And it served its purpose for pretty close to 100 years. So you cannot discount these guys for what they did. They really added something to the world of nuclear physics and helped us understand that little microscopic world. And it's a world we're still trying to figure out today. We don't really fully understand particle physics. We haven't reconciled it with quantum to a point with quantum mechanics, but we haven't reconciled the world in between that and relativity quite as well as everybody would like. There's still pieces of it unknown. In fact, there's still a search for this grand unified theory that even Einstein went to his deathbed trying to figure out how to unify all of physics, because there's still pieces of it that don't quite fit together. And we may never fully understand it, but we can get closer all the time. And the more we understand, the more we actually can do good things for both humanity and whatever else exists in the universe. So I hope you've enjoyed this video. We'll see you on the next one. Please don't forget to click subscribe and like, and we'll see you soon.